Welcome to the AI Research Roundup. I am Alex. Today is May 10th, 2025. We are looking at a research paper from Hugging Face's trending list, published just 6 days ago on May 4th, titled An Empirical Study of Qwen3 Quantization. This paper explores how well the powerful Qwen3 Large Language Models perform when compressed using low-bit quantization. This technique, it reduces the model size by using fewer bits for its internal numbers, making it suitable for devices with less memory. The study tests various post-training quantization methods, which are ways to compress models after they are already trained. Okay, so looking at how these methods perform, Figure 2 shows the zero-shot common-sense reasoning accuracy. This measures how well models reason on new tasks, without prior specific examples, across different Qwen3 model sizes. We see plots for techniques like activation-aware weight quantization, or AWQ, which considers neuron outputs during compression, then for GPTQ and BIL-M. Generally, larger models and higher weight bit widths, that is, using more bits for the model's internal numbers, achieve better accuracy. Performance at 8 or 16 bits is strong, but drops sharply at 3 bits or fewer, visually confirming the challenge of extreme compression. Alright, so moving from common sense reasoning to a more fundamental language task. Figure 1 here shows us the perplexity, or PPL, scores. Perplexity is a common way to measure how well a language model can predict a sequence of text. Basically, the lower the score, the better the model is at understanding and generating language. These plots compare activation-aware weight quantization, GPTQ, and BIL-M on the C4 dataset for Qwen3 base models. We can see that as the weight bit width decreases, especially down to 2 or 3 bits, the perplexity score jumps up quite a bit, indicating a drop in language modeling quality. Okay, so similar to an earlier look at common sense reasoning, Figure 4 here again shows zero-shot common sense reasoning accuracy. This tests how models reason about everyday situations without specific prior examples. We see plots for activation-aware weight quantization, GPTQ, BIL-M, and now also smooth-quant. Smooth-quant quantizes both model weights and activations, the outputs from internal processing units. For example, W8A. 8 means 8 bits for weights and 8 for activations. Generally, accuracy rises with larger models and more bits, but quantizing activations, even at 8 bits, shows some impact, underlining the challenge. So after looking at how these models reason, Figure 3 shifts our focus back to language modeling quality itself, specifically showing perplexity scores on the C4 dataset. And remember, a lower perplexity means the model is better at understanding and predicting text. These 4 plots, for activation-aware weight quantization, GPTQ, BIL-M, and smooth-quant, show how perplexity changes with Qwen3 model size and different bit widths. We consistently see that very low bit widths, like 2 or 3 bits for weights, or 4-bit quantization for both weights and activations with smooth-quant, lead to sharply higher perplexity, indicating a significant drop in performance. So, to wrap things up on this empirical study, it is clear that Qwen3 models handle quantization well at higher bit widths, like 8 bits, but performance really drops off at 4 bits and especially at 3 bits or fewer. This is particularly true for linguistic tasks, and when quantizing activations, the outputs of internal processing units, possibly due to what are called activation outliers and less internal redundancy in these advanced models. We also saw this trend in broad knowledge tests like MMLU, which stands for Massive Multitask Language Understanding. Thanks for tuning in to the AI Research Roundup.